Okay, welcome everyone. So we're looking at how we can define reaction rates or discuss reaction rates from the molecular point of view. And a useful equation that draws together all the questions of reaction rates, so meaning that collisions must happen, collisions need to have sufficient energy, and they must have the correct orientation for a reaction to be successful, is called the Arrhenius equation. So this equation um, allows us to connect the idea of the rate constant with the activation energy. And if we look at the features of this equation, so of course, like I said, so this is the rate constant. This is the activation energy. And this A here is a very important factor. We call it the frequency factor. Frequency factor. It is sometimes also called the pre-exponential factor. Pre-exponential factor. All right. And so if we discuss here, okay, of course you have the gas constant R and you have the temperature T. So do you see that this equation combines the ideas of what is the energy required for the reaction to proceed, what is the temperature at which this reaction takes place. Then it takes something called the frequency factor, which is an indication of how many collisions happen per second. So this frequency factor, um, it often has units of per second. So, or it always has units of per second. So it literally gives you an indication of something per second, and that equals then the rate constant. And the rate constant, of course, will have its own units, depending on what the order of the reaction is. So the equation combines all those ideas that we discussed. So like I said at the beginning, it combines the idea of that we need a specific number of collisions, which is given by the frequency factor. It combines the idea of that those collisions need to have sufficient energy and they need to have the correct orientation given by the activation energy and the temperature. And then we can use that useful information to determine what the rate constant is. And hence, the rate constant gives us an idea of what is the rate of the reaction. And altogether, that's just what we call the Arrhenius equation. And that was developed by savant Arrhenius, millions of years ago, just 100 years ago, um, who then determined the specific relationship between all these factors so that we can study rates of reactions using all these parameters. Okay, so there's some information that you can read. So we've just discussed it. It gives us a way to relate the activation energy and its temperature dependence with the rate constant. And then it also gives us a way to calculate the rate constant if we know the activation energy, temperature, and this frequency factor. Also important, we spoke a little bit about units, but the units of K, units, and A are the same. And why is that? Because everything in this top part will cancel, right? It's e to the power something, so that is a unitless quantity. And hence, its k is equal to a multiplied by a unitless quantity. So it means the units of k and a need to be the same. And that's why you can see the frequency factor gives you an indication of perhaps its molar per second. So it gives you concentration per second. And that literally then gives you an indication of what is the number of collisions per second, depending on the concentration, for example. And it gives you direct influence on the rate constant. Okay, so it's a very, very important equation. It's a very neat equation, and it summarizes all these dependencies that we've been looking at thus far. All right. Now your big question is probably, how do we determine any of these quantities? How do you measure, for example, the activation energy? How do you measure the rate constant? And the answer is, you will do some graphical determination, or you can use some graphical techniques. So if you were to take the natural logarithm, so in other words, if you take ln of k, so the ln of this entire equation, and you take ln of a e to the minus ea over rt, then you will get ln of a and ln of e to the minus ea rt, which then will reduce to minus ea over rt. And you can rewrite that in a form which you can interpret as a straight line, as y is equal to mx plus b, which you can then go ahead and plot on a graph to say, if I plot ln of k versus 1 over t, so see 1 over t is your x, ln k is your y, and then you should get a straight line which has a slope of what? What is your slope? You can identify the slope as minus ea over r, right? So the slope is going to give you the activation energy divided by r, or negative the activation energy divided by r. So what you do is you set up a bunch of reactions at different temperatures, and then you plot the ln of the rate constant against the inverse of temperature. And from that, you can then determine the activation energy for a reaction. So that's why this equation is very useful. You can, you can determine the activation energy from the slope then from that graph. Okay, so we'll look at an example of that specifically in class. And yeah, that's basically the usefulness of the Arrhenius equation. You can, of course, work the other way around. So you can. Right, now let's say, for example, you only had 2 points on this graph. So remember, these, if you were plotting this data, you would have several points. So many temperature points. But let's say, for example, you only had 2 points. Then in principle, something that you could do is you could use an algebraic method to determine the activation energy. So meaning you could take one set of K and T data and another set of K and T data. So right, K and T, and you can subtract the two from each other. So just notice that I took this formula, so ln K minus EA over T RT plus A, and I substituted in two sets, so K1 and T1 versus K2 and T2, and I substituted that in. And if you subtract those two things from each other, you can get an expression to calculate the activation energy from. Or if you know the activation energy, then you can calculate, really anything else in this equation. So this is if you have two sets of data of K and T data. All right. Or is something else. So meaning that you will have some sort of set where you know the temperature and the rate constant at one thing, and you know at least the temperature of something else, and you asked the activation energy or something. You'll have some combination of information that you will need to know. So this is a specific situation where you only have two sets of conditions. Then you can do it algebraically, and you don't need to do it graphically. All right, so that's the Arrhenius equation, and why it's useful and how you can connect it to the activation energy and the rate constant, and of course the temperature. All right, so I hope this was a useful little video, and I'll see you in the next one. Thank you for watching.